let's look at quadric surfaces, which are our three-dimensional equivalent of conic surfaces in 2 dimensions. In 2 dimensions, we have parabolas, hyperbolas, and ellipses. But in 3 dimensions, we will have paraboloids, ellipsoids, and hyperboloids. Let's start with paraboloids. For paraboloids, we need one variable to be linear and the other two to be quadratic. Examples include z equal to x squared plus y squared, or something like x is equal to 4y squared minus 7z squared. I have one linear variable and two quadratics. There are two fundamental shapes for paraboloids, and the trace can help us determine which it is. When we hold the linear variable constant, the resulting equation will describe either an ellipse or a hyperbola. Our first fundamental shape of paraboloids is elliptic paraboloids. For an elliptic paraboloid, I need my quadratic terms to be of the same sign. Things like z is equal to x squared plus y squared, y is equal to 3x squared plus 7z squared, or x is equal to 4y squared plus 2z squared. These would all be elliptic because when I solve for my linear variable, both of my quadratics will have the same sign. On the other hand, a hyperbolic paraboloid would be like z equal to x squared minus y squared, or y equal to negative 3x squared plus 7z squared, x equal to 4y squared minus 2z squared. My quadratic terms will have different signs once I solve for my linear variable. So let's consider z equal to x squared plus y squared. This one is going to be elliptic because my x and y term do have the same sign. And here's the graph of this paraboloid. We can definitely see the elliptic nature of it because it does look like it could be an ellipse if we continued it. On the other hand, let's consider z equal to 3x squared minus 5y squared. The fact that my x and y are different signs means this is going to be a hyperbolic paraboloid. And here's the graph of this function. We can see this saddle point happening where it kind of looks like a saddle at the point 0, 0. And this is what's causing it to be a hyperbolic paraboloid. Next up, let's look at ellipsoids. Ellipsoids will have all of our variables be quadratic and all the same sign whenever we have everything on one side of the equation. As an example, we can have x squared over 16 plus y squared over 25 plus z squared over 10 equal to 1. All of my quadratics are on the same side and they all have the same sign, which makes this an ellipse. If I look at the graph, I can see this here, where it does look like an ellipse in 3 dimensions. So this would be my ellipsoid. Next, let's look at 2x squared plus 7y squared plus z squared equal to 9. Here is this graph, and we can see the ellipse for this particular one. We have all of our terms quadratic and all the same sign, which gives me this ellipsoid shape. Finally, let's look at hyperboloids. Hyperboloids do have all of my terms, all of my variables quadratic, but this time they're not all the same sign like they are in an ellipse. Let's consider this one here, x squared minus y squared minus z squared equal to 1. And this right here is what it looks like. If we zoom in a little bit closer to the origin, We can see these two big cones, and they do have this space between them at the origin. This is known as a two-sheeted hyperboloid because there are two pieces to it. Next, let's consider negative x squared plus y squared plus z squared equal to 1. This time, my hyperboloid looks like this, and we can see how the two pieces are now connecting. This is known as a one-sheeted hyperboloid. So when I look at the equations, what's the difference? I want them to be equal to 1 each time, and you'll notice my one-sheeted has one negative sign, whereas my two-sheeted has two negative signs. And this is going to be the difference. Once I have this equal to 1, what's happening to my negatives? How many negative signs do I have? So my final question is, what about this one? Negative 17x squared plus 3y squared minus 8z squared equal to 0. This time, I can't set it equal to 1. I can't have my quadratics on one side and my numbers on another, since it has 0. So it looks like I have two negatives, but multiplying through by negative 1 would make me have one negative. So what happens here? Here's my graph, and if I look at what's happening right at the origin, it's kind of being pinched together right at the origin. It actually ends up being two cones that meet at the origin. And so that's what's happening when I can't set this equal to 1, is instead of having one or two sheets, I actually have two cones that are meeting at a singular point.
If you would like to see Professor Pierce make more videos like this one, you can support her on Patreon in the link below. Any and all support means a lot to her. It allows her not only to make more videos, but it also allows her to campaign for free and accessible online education to conferences and other universities. Thank you for watching, and remember, math is for everyone.